Welcome to the Trip experience. Trip is not simply a robust journey planner. Trip is a massive revolution in the world of traveling. With its displays of a set of journeys with different missing probabilities and arrival time, Trips let you choose the schedule that suits you the best. Here is an example of the typical use case of Trip, where the user enters the source and the target stop, as well as the desired time. While Trip computes the journeys and makes coffee, well, it actually computes the journeys at least, we will quickly describe how we gave birth to Trip. Our first attempt at journey planning was brute forcing the timetable by finding each trip connection a stop and each destination this trip could lead to. We quickly realized that this implementation was way too slow. After some research, we found CSA, Trip's Honorable Elder. CSA is a revolutionary algorithm in the world of journey planning that was published in 2013 by Julian Debel, Thomas Badger, Ben Strasser, and Dorothy Wagner. You will find their publication on GitLab if you are interested. It is particularly powerful since it doesn't need as much preprocessing as its predecessors and run in linear time of the number of connections, which can be computed from a timetable in a reasonable amount of time. Although this part can be considered preprocessing, it is in no common measure with the previous 2 weeks corresponding solution done by Google in 2009. Now that Trip has computed our journeys, we can see how the results would be displayed in a real-life case. For each journey, we can see it in the visualization displayed in a color related to the probability of missing a correspondence during this journey. We can click on any stop where we need to take a correspondence to display the stop name. The more the color leans towards green, the less likely we are to miss a correspondence while taking this journey. The closer to the red, the more likely we are to miss one. Let us talk now a bit more about our implementation. We will first explain our preprocessing choices and early issues encountered. In order to compute mean and standard deviation of lateness, the first question to arise was with respect to which criterion the computation had to be done. Plotting the accumulated lateness per the different possibilities, we observed that stop and trip ID criterion would be relevant ones. In order to perform this computation, we had to filter out the samples for which both departure time were not set, scheduled, and actual. We decided to only use departure time for this computation, as we made the hypothesis that it was likely that arrival times behave in a symmetric fashion. We had then access to a mapping from pairs stop trip ID to pairs of values mean standard deviation. From our initial implementation, we made an attempt at reducing the processing time by clustering the stops by their geolocalization. We found the geodata on Swiss Open Data and found out that the indexing was made by a feature we also had in our timetable, bprick. We later found out that there were both duplication of stop names and of bprick, which meant we had to make the choice of removing duplicates until both IDs had a one-to-one correspondence. Furthermore, many stops did not appear in the geodata as they were located outside of Switzerland, at the boundary. Since there were very few, we decided to focalize on stops inside Switzerland as they would cover most of our needs. The second main processing decision we made was to restrain ourselves to a 2-day time interval in the data for on-the-fly related timetables. We made the hypothesis that there were only slight changes in the timetables from one day in the year to another. This could be anyway easily computed when any change in the timetable is notified to any person maintaining the app. It represents a link between two stops at a given time. The connections are ordered by increasing departure time. This makes sure that at any point in the iteration, we know that we either can reach the connection or we cannot. For each connection, we check whether we already reached the departure stop in time, aka before departure time, and if so, check the destination's earliest time to see whether taking this connection represents an improvement in our journey inside the graph of stops. In order to take into account neighbor stops, stops that can be reached by foot from another stop, we pre-computed a dict of set which has an entry for each stop, and this entry contains pairs stop ID time. Each stop ID is the ID of a neighbor, and the associated time is the walking time needed to reach this stop. Each time we update the earliest arrival time of a stop, we also update the times of its neighbors with the according walking offset. In the original paper, the authors mentioned the Pareto optimal set of solutions improvement. However, we quickly find out that implementing such a solution would be far too costly. We instead choose the following trade-off. Computing probabilities at each change using our table, for each slice of probability from 80 to 100%, each 2%, we compute at each stop the earliest journey so far at this probability of missing no connection. The minimum probability as well as the slice size are arbitrary and changeable, but we thought that 80% was already bad enough, so we shouldn't consider even worse candidates. As the solution ran in roughly 6 minutes, we then made the following filtering on the connection using an early pre-run of the vanilla algorithm in order to remove the unreachable connection before our user's starting departure time or 10 hours after it, and at last journeys that would be made up of more than 5 correspondences. As future improvements for trip, if any exist, we would reduce the dimension of our mean standard table by clustering the accumulated delays by stop and trip ID. This would change the table size from 5,900 times 180,000 to an estimated size of less than 100 entries, since we expect roughly 5 clusters for the stops and 10 for the trip IDs. This improvement would greatly reduce the query time of each miss probabilities, which make for numerous calls during the algorithm run. The second improvement would be to consider journeys that take a connection we would usually miss, but that depart with a trip ID which has usual delay. Even if the probability would be slow, it still represents an alternative that could be viable in certain cases. At last, we could fill the missing departure arrival times by performing profiling of trips, stops, and fill by similarity using a system akin to a recommender system. We hope you enjoyed trip, and we will make use of it for our following trips. Thank you for your attention.